All right, so we can get started again. So one of the important questions I got during the break, which I think is worthwhile discussing, is the comparison to how do we do an analysis traditionally. So traditionally we would use a histogram. So let's say, yeah, it's a one-dimensional histogram, and which you build using simulations, right? So you would say, whatever, this is your prediction from the simulation. It looks simple, but like you don't know exactly what this distribution is going to be. And of course, it's not continuous. You are building the histogram more like that, right? And so each of they have a finite width, and you populate them. You simulate much more events than you're expecting in data, so that you can really get a good. You can minimize the stat uncertainty here, and you can really get an expected number of events for each bin. And then what do you do with data? Let's say you get some data here, you get like whatever 3 events, 4 events, and something, and then you get extra events here, and then fewer events here, and so on. How do you calculate likelihoods here? So you know that this is a counting experiment, so you have an expected number, and you have an observed number, so you can get a likelihood from Poisson, the Poisson distribution. This one, basically this, right? I think you've seen this before in the lectures, but just a quick reminder. So you would plug in the expected number of events from the simulation and then the observed from data, and that would give you a likelihood per bin. And then either you can multiply them or take the log and add them up together. And that's how you traditionally do these kind of statistical inference. So traditionally, the inference itself uses simulations. Typically, there are data-driven methods, but we're not going into that. But whereas here, you use the simulations for training, and then when you apply it on data, you no longer need to build these kind of histograms. So you can think of the neural network method as a, you can like start from here and approach the neural network method if you could reduce the bin size, right? So right now you have a few events in the same bin, and then the individual properties vanish. But if you make the bin smaller and smaller and smaller, at some point you have infinitely small bins. And there each event is treated independently, and then that's what we're getting. With the neural network, we're getting unbinned per event likelihoods, which you can either multiply or take the log and add them up. The other advantage is that this histogram is one-dimensional. So you could, in principle, imagine making a two-dimensional histogram or bigger. But they don't scale very well, because the larger you make a histogram, the more simulations you need to be able to populate all the bins. Whereas the neural network can handle many dimensions and give you likelihoods without running into this curse of dimensionality. Yeah, so this is an important, like the connection to how we traditionally do build likelihoods is, I think, quite important. Yeah. And yeah, okay. If you have more questions on like hypothesis tests and building test statistics and all, I'm happy to chat about that also during or after this session. I think. Okay. Cool. So where we had left off in the notebook was somewhere here. We managed to get. We managed to get the likelihoods predicted from the network, and they looked somewhat similar to the exact computation. And now we want to know, is that good enough or not? So how do you do that? Of course, we know that these likelihood ratios, I've talked about them, are useful for hypothesis testing and reweighting and so on. The first thing we're going to do is try to reproduce the plot we saw up here. So here we saw it with the true likelihood ratio. So let's do the same one with the neural network predicted likelihood ratios. So of course the you're gonna need new ones here. So we replace the true data sets with the predicted one. So yeah, I'll zoom in, but this is not hard. This you can solve on your own. What are we doing? What are we doing? We're just going up here. We're going to reproduce this plot, but instead of the likelihood ratios from analytical, you get from the network. So all you have to do is, okay, all you have to do is this data set is the true. You have to replace this one with the predicted one, right? So this LR, so you call this something else. I called it pred LM, the LR. And in this one, you replace this with this, right? These ones. That's all you have to do. And I think that's what I've done. Let's see if it works. So I want to change the label. So it's not true anymore. It's spread. Spread. So roughly, it seems to look the same, at least for me, as the plot before with the truth. That's encouraging. And now we're going to look at a diagnostic. All right, so besides your rock curve and all of that will look fine here. It will look like something. You'll get an AUC of something, I don't know, 0.8 or something. But that's not going to tell you how well your likelihoods are modeled. So how are you going to understand? Let's say the neural network does very well in like most of the phase space and completely misses the shape in one small part of the phase space, right? So then in data, if the event happens to be in that phase space, your likelihood ratio will be completely wrong and your entire paper that you produce will be wrong. So how do you ensure that's not the case? So you need to somehow check that the neural network is learning the true likelihood ratio throughout the entire phase space. So you need to be able to make plots in all the observables that you care about in all the phase space. So the answer is here, but if you think about it, how can you make plots with this? One key trick I told you about is the likelihood ratio can, apart from doing inference, can be used for reweighting, right? So you can kind of flip this model into a generative model. So if you have one data set, you can, and you believe that the likelihood ratios are correct, then you can morph one data set to another data set. Does that make sense? If it really learned the likelihood ratio, it should be able to reweight one data set to another by giving weights to each event, such that like if this event was less likely in standard model versus in the new physics, then it'll give it higher weights. If it's more abundant in standard model versus new physics, then it'll give it lower weights to suppress those kind of events. Right, so let's see if the our classifier is able to do that. So that's what I'm doing here. What am I doing? The weights that I'm defining is just the likelihood ratio. And I'm trying to reweight the standard model events to new physics. So the first histogram that I'm making is of the standard model data set itself, right? So y x test with y being 0 is standard model, 1 is new physics. But I'm making a third histogram. This one has weights, right? And the weights are simply the weights given by the likelihood ratio. And since I'm only interested in, so I'm only plotting the standard model events, so the y-test equals 0, and also for the weights, the y-test equals 0. But I'm weighting it such that I'm hoping that it'll look like the new physics distribution. Does that look satisfying? So I can then scrutinize and see, even in the tails, this reweighted distribution, the green one, if I didn't tell you it was actually standard model events, you would look at it and say that the green and the orange are probably coming from the same underlying distribution, right? They look very similar, which means that it's really learned the likelihood ratio, not just in this part of the observable and not just in that part, but everywhere that we look. This is just one observable because it's a 1D problem. When you have an ND problem, you need to do these kind of plots in every feature. And you'll find that sometimes it learns in 5 features and the 6th feature is missing something. So then, okay, so let's actually see that happen. Yeah. Yeah, here not, but in real life, yes. It is exactly that. It's a marginal. Yeah, so what can you do? You can't look at 10-dimensional distribution, but you can plot marginals, and luckily we know which observables are important. So we have some intuition, so we can look at those marginals. Another thing you can do is, if you believe that the classifier is learned very well, you could reweight your, okay, do the same thing, right? But instead of looking just at marginals, you can train a fresh classifier to separate the reweighted distribution from the new physics distribution. And if there's any difference, then you're hoping this classifier, so if you've trained a neural network, maybe you can train a BDT to separate them. And if that BDT catches some differences, that means your reweighting is not perfect. If your reweighting is not perfect, that means your likelihood ratio is not perfect. You can use these kind of tricks to try to find weaknesses. Yeah. Right. You have to provide a PDF, which we have done in the beginning, but you see that this plot is not done with any PDF. This is done from the neural network. Neural network has not been given any PDF. It learns from data. It constructs it in itself. Yeah, that's the whole point. If we needed the PDF of the Gaussian, this method would not scale. I'm only using the PDF to show you that the likelihood ratios are close. In real life, we don't have a PDF. Okay, this is a key tool in investigating your SBI models. To make sure that they're doing the right thing everywhere. If you do an SBI analysis, you will be looking at these kind of plots for months and months and months and fixing it. So and fixing it is its own art. So sometimes you'll see that like sharp distributions are not well modeled, while smooth distributions are. Then you need to fix it with pre-processing. Sometimes you'll see that that the number of jets type distributions are not well modeled. Then you need to find a better neural network architecture that can handle jets better, like a transformer, and so on. So depending on the problem you're having, your solution will be different, either pre-processing or architecture or getting more training data somewhere, so on. Okay, another important diagnostic plot is the calibration curve that we've seen in my slides before. So just a reminder, this is the score distribution output of the network for standard model and new physics, right? The red is new physics, blue is standard model. And you construct the calibration curve by looking at the neural network score and looking at the fraction. So if the neural network score is 0.2, you want to see if really the fraction of events that pass that are given this score are really is that 20% of them are standard model. No, 20% of them are new physics versus standard model. So you can plot this curve, and this is what you see. So the ideal is the blue line. Everything would be just perfectly calibrated. This orange line is what you actually get, and it's reasonably good, I would say. Like in most of the central region, it hugs the line. In the plot I showed you in the paper, in my slides, you see a more typical one where it's like it's like an S, almost an S curve. So this is already doing a lot better, but okay, it's a simple problem, so it does better. But even then, towards the extremes, it doesn't do very well, and this is a typical thing you see even in physics data sets, that is the extremes that you need to be very careful about. Yeah, but this is reasonably good. If you start your analysis with this curve, then it'll take you only a few months to fix everything. So that's good. Now let's see what would happen if your network wasn't so well trained. So let's go back. So this one is change this to code, this cell. And I've tried to construct a classifier that's going to hopefully be overtrained. And then let's try to see what the likelihood ratios do now. Okay, so this plot still looks kind of okay. But let's look at the actual diagnostics. This looks way too good. There is? You see it? I don't see it. Yeah, there is a systematic. Yeah, it's slightly shifted towards the right. That's right. But I was hoping it would be even worse. Let me try another training. I'm going to train on even smaller. Okay, yeah. So now you start to see that things are not working so well. So it's not totally stupid. The model is doing something. It can still do some separation. But the calibration curve looks pretty awful. And then the reweighting also doesn't look all that good, right? The green is, okay, somewhere in the in between blue and orange. Yeah, right. And these are standard model events, so it makes sense that it would by default be closer to the standard model. Then it's trying to push towards new physics, but the neural network is not good, so it's not done a good job. So this is a way you don't have to rely on AUC, where it's like not interpretable, whether 0.8 means that's just the best you can do or not. Here you can actually see that there's room for improvement. And there's room for improvement consistently throughout the whole phase space, because it's an easy problem, but often you'll see that like it's only one part of the phase space where things are not working well. Hopefully we'll see that when we do the same thing for a physics data set. Okay. Yeah. Yeah, that's a good question with no good answer. As little as possible. Yeah, this is far too much. Definitely for most of it should really be hugging this diagonal line. And the little fluctuations you see, okay, I'm being conservative, and I would say the fluctuation should be within the statistical uncertainties. Anything beyond that, you should be very careful. And usually, like, we won't just look at this plot, we'll look at the ratio plot at the bottom. That's how detailed we go in the calibration curve. Yeah. I mean, you should convince yourself first, because it's not clear that you can. So yeah, you should look at all of these. The calibration, like, if it's right, the calibration curve will be almost the blue line. If it's not, then it's a problem. And then these kind of reweighting plots that I told you about. You need to look at all of them. Then you need to look at the impact of systematic uncertainties, all of that. There's a lot. So your training is only one component of the analysis, right? The evaluation is very, very long and complicated. But it's worth it, because in the end, you get more out of the same data. You're able to get more information. Okay. Yeah, I'm happy to take more questions before we switch to the physics data set. How did I check the plot? So, okay. So what I'm doing here is I'm defining new weights. So I want to the idea is to reweight standard model to look like is that the question? Here, yeah. Ah, you mean the calibration curve? How do I make the calibration curve? Is that the question? What I changed is I trained the classifier again, and I did it on a very small sample size. So it was not very well trained. So I'm doing this just to show you an example of when things go horribly wrong. So here's what I changed. I didn't change anything down here. The only thing I changed is up here. Here. So this was how we trained it before, and this cell is how we're training it now. You can see here that the training set is much smaller. Okay. Overtrained on a small sample size. But if you increase the sample, you can train more. Okay. So just to get a feeling for how things would be much more challenging on a physics data set, we're going to use the same physics data set as yesterday's tutorial. And we're going to, because the distributions look similar enough, we're going to, what I'm going to define as H1 and H0 is not super realistic, but it's just useful enough to get a sense for things. So I think I'm putting background as H0 and signal as H1. In reality, it's good for this kind of a process. H0 is background only, and H1 is signal plus background. But if you do it that way, the training time is like many hours, and we wouldn't finish in this tutorial, so I've simplified it. Right. So just for fun, like for this exercise, H0 is B and H1 is signal. And so we're going to load the data same as yesterday. So oh, what is going on? Okay. So again, yeah, we've loaded the data. We've trained test plate. This is all bread and butter. Train a simple classifier. So we evaluate it. We calculate the likelihood ratio for the physics data set. Okay. And so, and then just to demonstrate, this is the typical curves you're used to seeing in normal classification. You would look at this rock curve, you would say, wow, it looks great. The training and test are almost similar. Everything looks great. Let's use this classifier. You would be done. And even this score distribution looks all right. Yeah. But if you use these new diagnostic plots that I'm talking about now, let's see how it looks. Okay, so this is for lepton PT0. We are reweighting the background to look like signal. Background is blue, signal is orange, and the green is the reweighting. And you can see that it's doing something. The green is closer to the orange one than it is to the blue one, right? But are you happy with this? It very much looks like, look, the green and the blue look significantly different still, especially in this, the peak region. And as I said, the peaky distributions are hard for neural networks to model very well. So you want to ideally do some kind of transformation here that makes this sharp distribution into a more broad distribution. So this kind of a thing, either you can solve just with better training or with better pre-processing. Right? So even though the regular distributions looked okay, and this model would already be fine if you were just doing a normal analysis where you use this to make cuts or whatever. If you want to do likelihood free inference, this model is not good enough. And then this is for lepton PT0. If you change the feature number to something else, I don't know, I'm going to try 4. Then you see that, okay, there's a lot of room for improvement even here, right? It's not, everything is not looking as nice as it was for the Gaussian example. And that's what you expect to see. So if you don't do very clever pre-processing and clever architectures and so on, then you won't get exactly the right likelihood ratios, which is what you need. So to your question of like, how do I convince other people? Yeah, it's important to look at these, convince yourself, and then, yeah. You have to do this anywhere, yeah. All the features for sure, but even other things, because this is doing multidimensional reweighting, which means you can even look at distributions that the features that you haven't given for training. Like if you've given phi1 and phi2, you can look at the distribution of phi1 minus phi2. And since it's this high dimensional reweighting, it should have for free given you a reweighting of this higher level variable as well. So yeah, sorry? Correlation. What kind of correlation? You mean like linear correlations? Yeah, you can look at that. Yeah, so instead of looking at plots, you can, you're asking, can I get metrics? Yeah. So you can get metrics. There's a whole research direction into how to automatically quantify plots. There's this really nice paper by these folks from UCSD on, so they do it for generative models. So the challenge for this is exactly the same as the challenge for generative models, which is, okay, now you have a model that does simulation, and I want to know, is it good enough or not? And you have to look at hundreds of plots, and no one has time for that. So they come up with, like, there are different metrics, like there's the old school way is chi-square, but that has some not very nice properties. So there are earth movers distance and Frischle distance. There are all kinds of these new distance metrics that we use. And there's this very nice paper that compares them all, and let me show you. Okay, I think, yeah, the firewall thing. I'm going to post this paper on Slack as well. In the general channel, maybe. Yeah, okay. So this is, I really like this paper that goes into a lot of detail. Let me show you one. So, so there are, okay, first of all, there are all these kind of different metrics and even more. There's the Wasserstein distance uh, that are used to try to separate, like tell the difference between two distributions, all right? Or to quantify the distance. And all of them have strengths and weaknesses. So these guys did like a thorough study. They said, let's say this is my truth. So they did it both for a Gaussian toy and for a physics problem. And and they wanted to see which metric captures all the distortions. So if this is your truth, then one distortion could be a shift. So you can see this plot over here is shifted. Another could be, let's say that instead of one Gaussian, you have two blobs, or two very far away blobs, or a bigger Gaussian, and so on. Right? So then they looked at different metrics, and they found that three of them were unbiased. One was the Wasserstein distance. This is called the Earth mover's distance. Yeah, I can get into it if someone is interested. There basically, and then there's the maximum mean discrepancy and the Frischler distance. There are the three most promising ones they found in this toy study, and then they did the same thing on jets. And here also they made very nice distortion. So from the true distribution of jets, they tried to, they did things like shifting. Let's see if they have a plot. Yeah, so they do smearing of the truth, shifting, removing the tail. So you can see the orange one has lost the tail. This is usually something that generative models often do. They don't model the tail properly. So it's important to see which metric captures that. And yeah, and then they evaluated on all of these data sets and then found, I think they recommend the Frischler distance as something that captures the distributions quite well. So it was a nice comprehensive comparison, and they found that in fact this does even better than a classifier test, which means if you train just a classifier and try to tell the two distributions apart, this is more robust than that, because the classifier test, you have to make sure that your classifier is correctly optimized and so on. So it's not apples for apples all the time. So these are metrics you could use also for our reweighting. So instead of staring at plots, you could look at these metrics, and maybe that will help you quickly evaluate your model and improve it. At some point, you have to look at the plots. I mean, unless CMS is completely different from Atlas, like we have to convince ourselves and our community, we have to show plots after plots after plots. Yeah, yes? You, yeah. Yeah, of course. So you can have distance metrics between one-dimensional distributions. And then if you're super confident that these are the only distributions I care about, then you're fine. Usually that's not the case. Usually you want also the correlation or some higher order. It could be something else, right? It could be some weird combination of them that gets you something useful. And then so that's why the classifier test was popular for a long time. The classifier test is just you take one distribution, another one, and you train a neural network. So it's in principle should capture all higher level correlations. But in practice, that can be a pain just because if you're comparing, let's say, three distributions and you train classifiers between two, it's possible that one classifier is just poorly trained compared to the other. Or so it's not a apples to apples comparison. It's very difficult to say that both the classifiers were trained and the hyperparameters were optimized correctly for each classification. And so, yeah, so this is useful. But of course, yeah, I agree with you that this is not the end of the story. And I think this is a very good first paper in this direction. And there are people working on generalizing it even more, trying to get, not just one thing is to quantify the difference, including these higher level correlations. The other is interpretability, because if you just give me a number that's a 0.8, what does that mean? Which of these features did not model well? So we want something that not only catches differences, but tells us this is the phase space where you need to improve your model. This is an open field, by the way. Like very little work has been done. If you have any ideas on how to statistically tell the difference between distributions, or with or without machine learning, it's like, yeah, a hot topic. Okay. Where are we? Okay. So after this plot, we have the calibration curve. And this time I've plotted both the training set and the test set calibration, and you can see that they don't match. So there are three problems here. One is, what is going on with this wavy stuff? To be honest, it's still not as bad as what you saw in my slides, where you get the S-shaped type curve, but still it's a funny behavior. And ideally, you want to put stat uncertainties here. And then you want to try to get this, at least in the center, it should really be hugging the blue line. And also the difference between the train and test is concerning. You want to make sure things are working fine. Okay, so now I want you guys to see, you can clearly see that on the physics data set, this classifier looks okay, but it's not good enough for SBI. So I would like you to try to improve it. You can do pre-processing. You've learned a lot of stuff over this week, so you can try to improve the architecture. You can, I would say, start with pre-processing and see if you can beat the default that we have here. So are you guys familiar with all the typical pre-processing methods? So one is the standard scalar, right? You shift the mean and standard deviation. Can someone suggest another kind of pre-processing? Min-max, okay. Min-max, these are all, yeah, trying to center your distributions. Is there any other kind of transformation you can do? Sometimes for energies, we do log transformations, which makes a very, yeah, it can really change the shape of the distribution, right? Yes, that's right. That's right. Yeah, you can take the log and then center it, and then sometimes that helps the training. Yeah. So if your distribution is funny shaped and long tail, bulk is over here and you have a long tail or something, or where like this is really like physics driven, right? And you think that it's more important for the network to capture this part of the distribution compared to the other. You can do a log transformation and make the whole thing look a bit more well behaved. Neural networks work very well when things are Gaussian distributed. And they work not so well when things have long tails and so on.
Instead of Mike, let me draw this example.
Yeah.
Which you often find, you still have to talk here. Okay, you often find in a linear scale versus number of particles, some distribution like this as a PT, okay. And once you transform this into log, it will be much more well spread like this. And once these are still positive numbers, modulo in the log case, whatever is below 1 has now become negative numbers, right? And then if you do a mu and sigma shift, where the mu and sigma is on the log distribution, then this is kind of a, if this is the 0, this distribution is well behaved like this. So this kind of two-step pre-processing works quite well. And for a neural network, these distributions are easier to learn.
Yeah, and this is particularly true, as we said, for neural networks compared to BDTs, because BDTs fundamentally are making cuts. So they can, if it's like this, they can make a cut here and cut everything away. Neural networks, there's been a lot of research into how you initialize the network and so on, and this is taken care of by PyTorch or Keras for you. But nonetheless, roughly the weights are initialized somewhere near this 0, right? You don't get initial weights at 1000. So neural networks train the best when the data is also somewhere between in this region, on both sides of 0 and not extreme. Like roughly a Gaussian centered at 0 and standard deviation of 1 is the ideal kind of data for neural networks to learn on.
Would you suggest that for PT and energy, instead of training on those variables directly, we train on the log of those variables?
Usually it's better.
I think before writing any neural network, the best practice is make the distributions of all the features you're using.
Yeah.
And if you see their numerical numbers are widely well spread and there is a large skewness in the distribution, think what kind of transformation you will make to those variables, which will bring them on the same scale. If you plot on a normalized canvas, they will more or less have the similar kind of shapes. And once you can make that transformation, it's far easier for a neural network to learn. Otherwise, it will screw up by default.
Yes. So whatever features you have, in the end, as much as you can, you want it to look like that. Okay, with the standard deviation is 1 and the mean is 0. So whatever pre-processing you have to do to make it so is usually going to be right, except if you're doing some really contorted pre-processing which screws up everything else, then no. But usually this is what you want. And especially for simulation-based inference, you really need your input variables to look like this.
It's also important to put the same pre-processing, the training, testing.
For sure. Yes. Yeah, so you guys can see, make plots of the input variables. And if one of you or a few of you can post it on Slack, then we can all see it. And then try to do a pre-processing, and if you can show before, after, and then how that improves or doesn't improve your network, that would be very nice. Yes.
So this log pre-processing has to be done for all the energies, right? Or like is it general for any kind of distribution?
So this obviously is not good. And so I think the first thing you should do is, as Sanmay said, just plot all the input variables. And you've done that. Nice.
So if I just do the log,
Yeah, so
then I have to.
so this looks already better, no? And then you want to center it. So center it at 4. You want to, so you can just do min max. No, not min max. Just do a standard scalar. So first do the log on whatever relevant variables, then do a standard scalar, and and then see how that affects. But yeah, remember to fit on the training set and do exactly the same on the test set. Yeah. You can see, yeah, there are arguments not to do that as well. But it's fine. But when you just substructure, I think I have also used log PT to improve the performance. But yeah, I guess it's. Are you saying that the uncertainties would be So if you could factorize that, it would be ideal. If you can like improve the network and then quantify the uncertainties. I don't know how to do that. But the thing is, like, if you don't do the log transform, it's not like the network is not learning that information.
But if you take log, how come like the lower part are also becoming the softer part is spread over a large number of parts.
Yeah, that's the thing.
And the harder part is squeezed into similar. So you don't want it to spread over because there's a more finer structure you are looking there, more total structure you are looking over there, but you want it to do that. Yeah, anything that makes the variation slow is sufficient, like square root. Yeah, okay. For IMSc,
Yeah. Divide by 0. Yeah, that's because this term is probably, so your y pred for something is exactly, it's exactly 1. So it's becoming a divide by 0. This happens if the network is super duper confident that this event is coming only from this data set. There's no chance it's coming from the other one. That would happen if the two distributions don't have a common support. I would be a little bit surprised because I looked at the distributions and they were not like that, but it's possible that I missed something. So, I mean, right now it's just a warning and you can ignore it, but if it starts to become a serious problem, then we can have a look. So the real thing is the hack I've done is I've treated background as H0 and signal as H1, which is not the right thing to do. Actually, I should do B versus S plus B. And there, the support will be the same. Yeah, and then you wouldn't have this problem. But then you're training, you need much more sophisticated neural networks and more training and all of that. And we wouldn't compute it, yeah. So for now, let's just ignore this and see if it's a serious problem, let me know and then. Can you take over for 5 minutes? I just want to drink some water.
Yeah. Just turn it off.
Okay.
Otherwise, we will hear.
Fair enough. So I'm curious, now we've waited a little bit. Has anyone managed to get a better classifier than the default? Sorry? Yeah, it's slow, it's slow. Okay. Fine, I'll wait. But now I'm waiting on your results. Um,
My computer hung
Ah.
negative.
Yeah, that's wait. It cannot be negative.
How is it reweighing? It means some
Cannot
weights are
be.
negative.
No, it cannot be. Weights cannot be negative. Can you look at the event there? What is the weight? So I guess you can just look at the weights. Sorry, the
This
yeah,
prediction.
yeah. Just have a look at. I mean, they cannot be negative weights. So you can just have a look at them, and so you can just say
This one.
yeah, less than 0, and see if there's any.
Mouse doesn't work. Stupid stuff.
Yeah,
And then
and then the same thing, less than 0. No. So why is it going below 0?
arbitrary units, electron PT.
No, it doesn't make sense. That's so weird.
No, okay. Maybe the first one I should look for.
Ah, yeah, the original has maybe has negative weights. Yeah, it does. I know it does. Yeah, okay, that's the reason. Okay, cool.
So they get enhanced in a more negative direction.
Yeah, and to the point where it's found a phase. Yeah, the negative weights have been enhanced more than the positive weights in the same region.
And then, yeah.
Yeah, it's weird. So this is definitely a problem. So you shouldn't be happy with this network. Yeah. Could be. Which feature were you looking at? Which feature is this? I don't have that effect. Yeah. But that's funny. That means the network treats, yeah, somehow manages to find these negative weights and enhances them more than the same events in the same phase space with positive weights.
To prevent a negative PT and push it to a positive. You have on the x-axis negative.
Yeah.
The x-axis you have negative.
But this is the weights.
But this is the weights.
Yeah, so this is like the y-axis going negative should.
That's the y-axis pure weights.
Yeah, that's weird. That shouldn't happen. That's unphysical.
That means the area under the curve is not preserved.
Yeah, it's weird.
So this reweighing procedure is not area conserving.
I mean, these are all plotted with density equals 1. So at least the plots are conserving area. The reweighting doesn't, since you're training with equal weights.
No, okay, actually, weighting procedure assumes that there are no negative.
No, it can handle negative weights, no problem.
Inherently assuming, because if I just scale things like here and so negative weight scaling up means my area is going down.
Yeah.
So something has to scale up.
Yeah, so the positive weights in the same phase space should go up. So in principle, the reweighting should, if they're in the same phase space, there's a negative event and two positive events, then it should reweight them both the same way, the scale them, so the compensation should remain the same. But it's not happening. That means it's treating the negative weights differently from the positive weighted events. So either those events are actually not in the same phase space, or the network.
Other part of this is just one variable. Other part of this is they have to do something.
Yeah. Yeah, so like when you do when we do SBI, sometimes the problem is not even in the network; it's in the we realize the data set is not good, and it has some unphysical features, and then we have to remove that part from the training to make things work. Okay, I think I will give you more time. and you can try to improve it, but I understand the training time is a bit long, so let's move on for the time being. As soon as someone has interesting results, feel free to post on Slack even after the session is over if you feel like playing around with this. I think it's a good exercise. And oh yeah, you have something? Yeah. Scaled meaning? Is it normalized? It's probably, it should be. Yeah, because I scaled both the training and the test sets, yes. Yes, it's scaled, that's right. It's not in GeV units or whatever, yeah. Yeah, so in principle, to make these plots, I should undo inverse transform before making the plots, yeah. If I want to see the correct units, yeah. Yeah, okay. Anyway, so yeah, please post your results on the Slack. You can definitely do better than what I've shown. Okay. Meanwhile, I want to leave you with some comments on uncertainties, which I want to cover in the last roughly 30 minutes that I have. Are we ready? Yeah, okay. Yes, okay. People seem settled down. All right. So everything I showed you now is without, we're pretending there are no systematic uncertainties. And of course, there was already a comment about, wait, what about theory uncertainties that you're not taking into account? So yeah, these are all in a real, in an actual Atlas or CMS analysis, you have to care about uncertainties, and we care about them a lot. Yeah, so it's machine learning. So when we started off, when machine learning became a major thing in HEP about 10 years ago, there was a lot of fear on what if these models learn aspects that are not well modeled in the simulation. So there was yeah, and this is a very legitimate fear that we're giving up control and the models might learn unphysical things and then it'll screw up on data. But since then, there's been a lot of work, first of all, to try to handle some of these kind of uncertainties, to remove sensitivity to them, but also in the other direction on actually using machine learning to improve the way we handle uncertainties beyond what we could do in the traditional techniques. So I will talk about some of them. And then the question in the end of like, how do we incorporate this with SBI is something that is a research topic right now. Of course, as I said, in principle, you can just put in the nuisance parameters as additional inputs to the network, and it'll give you the likelihood as a function of not just the parameter of interest, but also the nuisance parameter. In practice, this is not possible to do when you have a whole bunch of nuisance parameters. So we have a lot of people thinking about how to practically incorporate nuisance parameters. I will first talk to you about how to do it in a traditional, more traditional methods where you construct observables using machine learning, but then you put them back into a histogram and do the fit using histograms. And then we can wonder about how to combine SBI with uncertainties. All right. Yeah, so traditionally, what do you do? When, let's say, you're doing a histogram analysis, and you have this kind of a distribution. So the signal shape, there's this region where you're very sensitive to the signal shape, but unfortunately, you're also very sensitive to background modeling uncertainty. So there are these three lines that I'm showing are three possible variations of what the background could be, and you don't know which one is the truth. So if you do an infinite, one extreme is this infinite bin analysis where you're super sensitive to the signal, but also super sensitive to the background. And the other extreme is a single bin analysis. Now, you are insensitive to the background shape uncertainty, right? Because as long as all of them predict the same total cross section, it doesn't matter what the shape was. I just flattened it all out into one bin. And now I sacrifice sensitivity to signal, but I am super robust to background uncertainties. So traditionally, we would either, if this observable is not well modeled, we don't use it for analysis. Or we say, okay, it's not well modeled in the low PT region, so we block out that region and only use it for IPT or something like that. And so there is actually a machine learning equivalent to this. The problem, like these kind of solutions come from the field of domain adaptation. So here, this is now quite an old paper, but the question they're trying to solve is, if my training data set is only the source, so I have handwritten digits in white over black, but when I want to apply it, I'm going to have all of these colorful images. The fundamental problem is the same, but there is this superfluous additions, and I want my network to learn the salient features from the source data set without getting distracted by the colors in the target data set. So how do we do that? Yeah, so there were these ideas of adversarial training. This looks similar to a GAN, but it's not a GAN. And so here you have two neural networks. The first is the classifier. This is doing the actual job you care about, signal versus background. And then the second one is trying to regress the nuisance parameter. So if your classification is sensitive to the nuisance parameter and dependent on this nuisance parameter, then it would be possible just from the output of the classifier to guess better than random what the true value of the nuisance parameter was in the simulation. And if you can do that, then that means your classifier is biased. And then, the idea here was that you penalize the classifier every time the regression network succeeds. So as its combined target is this combined loss function, whereas the loss, this is binary cross entropy coming from the classification task, and this adversarial loss, which is basically it tells it that you need to be able to fool this second network in order to succeed. So in practice, in this very nice paper, Learning to Pivot, what they showed is, if this is your output of your classifier traditionally, right? So it's going to have a different distribution for data coming from different values of the nuisance parameter. So the blue, green, and red are different simulations at different fixed values of the nuisance parameter. And then your decision function is like that. Now after decorrelation, this adversarial training, the output of your classifier will look similar for all three data sets. And so the decision function really becomes like this. So it's the same for different values of z, where z is your nuisance parameter. So what is a nuisance parameter? It's something like a jet energy scale or tau energy scale or any of your experimental uncertainties, continuous values. Right. So I just want to make sure, like, are we still on the same page? Nuisance parameters is something everyone understands? Yes, good. So yeah, so nuisance parameters are like, so when we do statistical fits, there are things called parameters of interest. These are the things we care about, like the signal strength of the Higgs or some other theory parameter we want to measure. And we only care about these parameters. But then there are these nuisance parameters that we cannot ignore. We don't actually care about them, but they will affect our measurement. So for example, the jet energy scale. So we might, so maybe like we're measuring the jet, right? So we don't measure all the energy of a jet and then we calibrate to get it right. And let's say that we're measuring all the jet energy is, I don't know, like something like this, all right? But we have systematically undermeasured all of them. So the true distribution is actually like that, all right? So less here and more there. Or it could be the other way around, where, right? So there's going to be a systematic bias. All your jets are overmeasured by a little bit or undermeasured by a little bit. And so this we parameterize as a nuisance parameter. So this uncertainty in a calibration goes in as another parameter of the fit. So we want the data to tell us both what explains what values of the parameter of interest as well as what values of the nuisance parameter explain our data the best. So we fit them together, and yeah. Okay. And so of course, if you can make an analysis method that looks exactly the same regardless of the jet energy scale, then you're super robust to jet energy scale. But if you think about it, any analysis technique that you do that is completely unbiased to jet energy scale is actually not using jet energy information very well, right? So if you know that your analysis needs jet PT information or something, then you know that you're sacrificing your power. So then comes the question, what if we could actually do better? Instead of being completely invariant to these uncertainties, the fact is that we actually have a prior on these nuisance parameters. So we might not know exactly what the jet energy scale is, but we do control region studies. We do try to measure this. So we have we usually say that we have some like best guess with some uncertainty on these nuisance parameters. So why don't we somehow use this information to better do a measurement? So ideally, like if you had a simple problem, a two-dimensional problem, your signal is concentrated on the top right, background on the bottom left, and then your nuisance parameter is this angle, right? It's pi/4 for a nominal case, but it could be different, and then your optimal decision function, which is a diagonal here, would change. It would become something like this or something like that, right? And normally what we do is we optimize our analysis at the nominal value, and then we hope for the best. Like we make sure that things would still work kind of fine on the nuisance for other values of the nuisance parameter, but we don't re-optimize the analysis for other values of the nuisance parameter. But ideally, if we could, we would. Then we would say that for this nuisance parameter, we would have this kind of a cut and that kind of a cut, and then use also this prior that we have to somehow incorporate all of this information and get a likelihood in 2 dimensions as a function of the parameter of interest and the nuisance parameter. This is what we would want to do. That optimizing the analysis in one part is hard enough. Doing it for many different values, in fact, an infinite number of values is like next to impossible, unless, of course, the whole thing is automized, which you can do now with neural networks. So quite similar to what we talked about earlier. If you're going to train a normal classifier, you could just add one input to it, which is the nuisance parameter, and then it becomes an uncertainty-aware classifier, which can optimize its decision function for different values of the nuisance parameter. At this point, you should be worried. You should say, wait a minute, you know only the nuisance parameters in simulation. You don't know it in data, so how is this going to work? So I'm going to answer that question. But for now, the intuition is that you allow the analysis itself to vary as a function of the nuisance parameter. And so whatever the true value is, you will have one version of the analysis that is optimized for that value of the nuisance parameter. And then you can use the prior. Okay, so how does that look? Again, in this 2D simple problem, you have this is what you would usually have. You would optimize your classifier in this nominal case where the decision function is diagonal. And then your data is also distributed that way. So you get the best AUC possible, which is this. This is like analytically done. So this is really the upper limit of how well your classifier can do. And our uncertainty-aware classifier also produces the same optimal result for the nominal case. Now for the systematic up case, where let's say this angle has been changed to pi by what is this? Yeah, basically rotate by 45 degrees, pi/4. Then your data is distributed vertically, right? But your standard classifier is still the decision function is frozen diagonally. So it's suboptimal, and then your AUC drops a little bit. Whereas the uncertainty-aware classifier, as soon as you give it the correct value, it rotates its decision function and regains the optimality. So it's the same as in the nominal case for this problem. Okay. So what do we do in collision data where we don't know the true value of the nuisance parameter? The answer is we don't try to guess one. We scan over all possible values. So what we do is this is your observed data. You don't know the value of z. But this is your simulations at different values of z, 0, pi/4, pi/2. And you see what the signal and background distributions would look like in each of these cases. And then you compare the data to each of these template histograms. And you can calculate this likelihood in 2 dimensions, right? And of course, each of these histograms is plotted with a different value of z going in as an input to the network. So here it's really pi by 2, pi by 4, 0. And what do you do with the observed data? You evaluate it many, many times. Once you evaluate it, assuming z equals pi by 2. Again, you evaluate it with pi by 4, and then you compare it to this histogram. Then you evaluate it with z equals 0, and you compare it to this histogram. That's how you compute this likelihood thing. And then the next step is what's called profiling. It's a standard statistical method to that basically what you're doing is you only care about the mu in the end, so you're going to profile away this z dimension so that so that you can look at the likelihood curve as in the parameter of interest. This is what you're seeing. This is a typical negative log likelihood curve. They're always on the Asimov data set, which is the representative data set. They always minimize at the true value. So what you actually care about is the width of this parabola. And the narrower the width, the smaller your final uncertainties will be. This parabola includes both the statistical and the systematic uncertainties. And you can see that this uncertainty aware classifier that I talked about, even though you didn't need to know the true value of the nuisance parameter in data, just because you were able to scan over all possible values, it actually ends up doing better than any of the other methods compared, including this decorrelation method that I talked about earlier, adversarial training, or there's another method called data augmentation, where instead of training your classifier on only nominal, you train it on all of them. But this one clearly does much, much better. Of course, this is on a toy problem. Okay, I'm going to show this also on a physics data set, but any questions up till now? This does not work in theory. Nothing works in theory uncertainties as far as I can tell. This is like one of the things if I can solve a ML for theory uncertainties, I will be very happy with myself. If it's something you think about, we should chat about it afterwards. Yeah. Hmm? Yes. Yeah, I didn't talk about it. It's here. So this is your Poisson from the histogram. This is your prior Gaussian prior. Absolutely. And yeah, this is a Gaussian prior. If instead you want to do a simultaneous fit with some control region, you can do that also. That's also in the paper. But yeah. Sorry, can you speak a bit louder? Yes, this is tau. Oh no, sorry. This is the right. Where is it? There. This is Z. So this is the toy problem. So the Z is telling you this angle. So when Z is pi by 4, it looks like this. When it's a different angle, the signal rotates and the background goes up. This is nominal. I'm calling it nominal. Like it's our, yeah. So let's say like my best guess, I've done an auxiliary measurement. My best guess is that Z is equal to pi by 4. And then if it goes up to pi by 2, I call it systematic up. And if it goes to Z equals 0, I call it down. So these are somewhere in the middle. I don't know what the values are. But if it was, if this red circle was over here, it would be pi by 2. And I would call that syst up. Okay. Okay. Then, of course, if you just show this on toy problems, nobody's going to be excited. So this is also applied on the Higgs ML data set, where we use tau energy scale as the nuisance parameter. So this is how the tau energy scale affects the different observables. So you can see that the nominal is the orange one, and then if you decrease it by 10%, you get the blue curves. And if you increase it by 10%, you get the green curves. So you can see that all the features systematically shift if you change the tau energy scale. And then, yeah, we do the same procedure, and I'm directly showing you the final result. So this is tested. The method is being tested where the true value of mu is equal to 1, and the true value of the nuisance parameter is not nominal. It's at 0.8, so 20% below the nominal. And we see that the green one is narrower than the other methods. The differences are now smaller because this data set is stat limited. The more systematic limited you are, the more this method will help you improve over your state of the art. And in fact, here I should also show the black one. This is the best you can do. So this is if you knew the nuisance parameter perfectly well and trained a classifier on only the data set with the true value of the nuisance parameter. We see that it so happens that in this case, the uncertainty aware classifier does just as well. It's not always going to be the case, but in this case, it's quite nice to see that. And yeah, we have the ratio plot showing that. And just to make sure that this is not a feature only of this one particular value of the nuisance parameter, it remains true for the nominal case and for the systematic up case. And no matter where you check, the green always does as well as the locally optimal classifier. Okay. I want to make one comment here, which is that now, what does this mean in a real analysis? In an actual CMS analysis, you'll have one or two dominant sources of systematic uncertainties. And as I said, this is useful only in experimental uncertainties. So if you have something like a jet energy scale or a B-tagging efficiency or something, you can use this. And you will have 50 other nuisance parameters that have a minor effect. And it's not possible to train the network on all of these nuisance parameters. But the nice thing about this is that this relies on traditional histograms to do the final likelihood, which means that you can treat all the other nuisance parameters the way you would in a normal fit, while the dominant sources of uncertainties can be parameterized. This is not the case once you do SBI, because in SBI, the likelihood comes not from the histogram, but from the network. So really, the network needs to know about all the nuisance parameters. Okay. An interesting thing is when we put out these results, after that, some of the machine learning researchers we talked to found this quite interesting, because from the way they do their studies, they assume all samples are IID, right? So there's no information you can get from correlations between two events. Two events are always independent, right? And that's something we assume as well, but not really, because clearly this technique is benefiting from the fact that all events are correlated in the sense that the nuisance parameter affects them in the same way. The nuisance parameter is the same for all of them. Just like the parameter of interest is the same for all of them. Does that make sense? The jet energy scale biases all events in the same way, and that's something we can exploit. So the machine learning researchers found this quite interesting, and a few months later, we saw this paper come out of the ML world, which I found very, very nice. So this is unrelated from my paper, but similar idea. So this is a handwriting recognition problem, right? And usually, the way this works is people have handwritten text from thousands of people, and the classifier is trained on all of these images to try to do handwriting recognition. Of course, this for you might look like an A, right, in your handwriting. In my handwriting, this is the number 2, because I have terrible handwriting. So, and this is, it's a stylistic thing, right? So each person, if you look at each person's handwriting and you first adjust for that, you will probably do better at reading a letter. So if let's say you want to read your doctor's prescription or something, then all the letters in this protest thing, all the letters are correlated because they're all written by the same person. So in fact, you don't want to be invariant to the differences between people's handwriting. Then you lose classification power. Instead, you want to be adaptive. You want to take into account the fact that there's a correlation between each of the letters, and as it's been written by the same person. And they call this adaptive risk minimization, and it's a machine learning method that managed to improve handwriting recognition by exploiting these correlations. This is a very nice mirror to the kind of uncertainty aware stuff we were talking about. Okay, yeah, so final comment, this is the theory uncertainty thing. So it's very exciting to go from the point where we said, oh no, ML will screw things up when we have uncertainties, to actually ML can help us better treat uncertainties. But we shouldn't go too far in that direction. So it's very tempting to then use ML also to handle theory uncertainties. For example, we have this typical one, hadronization. We really, it's one of the worst to model uncertainties. So what we do in experiments sometimes is we look at the difference in analysis performance on Pythia, which is one simulator, versus Herwig, which is another simulator. Both of them each uses a different way of doing hadronization, and neither of them claims to be perfect. So we kind of take the difference between the two, and we say that's our hadronization modeling uncertainty, right? But there's actually no reason to think that like in an experimental uncertainty, you can actually interpret something as a 1 sigma or something. But here, this is just an ad hoc estimate. And then if you remember the decorrelation we talked about, if you try to apply that here and say, hey, Mr. AI, can you please reduce the difference in your performance between Pythia and Herwig? Because I'm using this distance to estimate my uncertainty in this n-dimensional ball, right? Because I don't even know what the dimensionality of this theory space is. But I know that like Sherpa also uses, I think, one of the models, either cluster or string, but in a different setting, so it gives you slightly different hadronization. And you're hoping that nature lies somewhere in this uncertainty. And then if you can shrink the difference in your response to Pythia and Herwig, you're hoping this ball shrinks, and then your response to nature is also within this ball. But what the model will do is it will do exactly what you ask it to do. It will only reduce this one-dimensional distance, and then everything else lies way outside this uncertainty. So the model has only learned to fool you rather than actually shrinking these uncertainties. And we show this in this paper for a couple of situations. One is hadronization, another one is scale variation uncertainties, where by doing machine learning, you only fool yourself. You think you reduce the uncertainties. Actually, sometimes either it's the same or in fact it's increased. It's quite random. And so this is something, I guess you often relearn things that humanity has invented before. The economists call this the Goodhart's law, which is when a measure becomes a target of optimization, it ceases to be a useful measure in itself. And that's true for any proxy metric. If you believe your metric, you can optimize it. But if it's like this ad hoc estimate of uncertainties, like this hadronization thing, then you should probably not try to optimize it unless you have a very clear idea of how to go about this in a way that will generalize to the actual problem. Right. So just the final comments on uncertainties is that uncertainty-aware SBI, in principle, we have a way to do it. In practice, there's still more work to be done, and hopefully we will see in a few years us being able to actually handle an order of 50 or 100 nuisance parameters with SBI. Because, yeah, the challenge is, first of all, generating the training data set that populates this entire phase space, and training the model and validating it. So, yeah, this is an open question, topic of research. How do we make SBI also uncertainty aware in a meaningful way? By default, it could work, but how do we make it practical? Okay. Yeah. Thank you. I think I've ended exactly on time.